Hello everyone, and welcome to this virtual lecture course on Quantum Condensed Matter Physics. I'm Dr. Andrew Mitchell, and in this lecture we'll be studying models of simple spin systems. This will build upon the work we did in the previous lecture developing the formalism for spin systems. In the first part we're going to look at a simple system of two spin-half particles, and we'll actually see that these can combine to make a triplet, a spin-1 object. We'll study this in detail, and we'll actually see that the triplet state of two spin-half particles is actually identical mathematically to a genuine spin-1 particle. The operator algebra is the same, the observables are exactly the same, everything is the same. So we can actually, in some sense, regard a spin-1 particle as being made up out of two spin-half particles in a triplet combination. And actually, this will come out as something interesting and useful to us later on in the course when we talk about fractionalization and the Haldane spin gap. In this lecture, we're going to talk quite a lot about quantum numbers. We'll see that quantum numbers are conserved quantities that are not changed by a Hamiltonian. When the Hamiltonian acts upon an eigenstate labelled by particular quantum numbers, they are not changed by the action of the Hamiltonian. They are conserved through the dynamics of the system's evolution according to the Hamiltonian. There is a corresponding operator for each quantum number, and a conserved quantity corresponding to such a quantum number is one where this operator commutes with the Hamiltonian, and we'll be discussing that in this lecture. Specifically, we'll be talking about the spin and spin projection quantum numbers, individually for each spin in our system, and also the global spin and the global spin projection. We'll talk about simple models of spin systems, especially the Heisenberg exchange model. We'll talk about the microscopic origins of the exchange interaction, and we'll see where that comes from and what role it plays. For a simple system involving two spin-half particles, we'll see that the exchange interaction can actually be written in terms of the total spin quantum number, and therefore we can trivially write down our eigenstates and eigenenergies of this system in terms of those quantum numbers. We'll see that the energies of the three components of our spin-1 triplet are degenerate, but these can be lifted by applying a magnetic field, and we'll talk about simple systems like this in this lecture. Towards the end, we'll talk about the more general case of Heisenberg spin systems involving many spins, and we'll see that life is not so simple in that case, and that we need a more direct way of solving the Schrödinger equation for such systems, and that will actually come in the next lecture. So let's get down to work.
In this lecture, we will continue with the analysis of the two-spin system, but first let's recap some of the formalism that we developed in the previous lecture. First, we consider two spin-half particles labelled A and B. Each of these spin-half particles can have a z projection of the spin which is either up or down, denoted here by these cartoon arrows up and down. We label the z projection of the spin of particle I by SZI, and it can take values of either plus a half or minus a half. In this case, I labels either the A or B spins. Now we consider the combined AB system, which has a larger Hilbert space. It has a Hilbert space now of dimension 4, because we have 4 different possibilities for combining the two spins. We can enumerate a suitable basis from product states of the complex vector spaces from A and B spins. What I mean by that is that I can write a single ket for the combined system with up-up, denoting that there is an upspin in A and an upspin in B, and this is just obtained from taking the direct product of the state of A with an upspin with the state of B, also with an upspin. Similarly, we have states of our combined AB system corresponding to up-down, down-up, and down-down states. This is the full space of possibilities of our combined AB system for two spin-half particles in the product state basis. We call this the product state basis because the states of the combined system are simply obtained by taking the product of the states of the individual subsystems A and B. But of course, in quantum mechanics, this is not the only option. We can also have linear combinations or superpositions of these basis states. A given system, described by a given Hamiltonian, may have eigenstates which are linear combinations of these basis states. The product states that I've written down here constituting this basis are actually kind of like classical states because they are not entangled. As we will see, quantum mechanical entanglement arises from the superposition of states. We will quantify this in the next lecture in terms of the entanglement entropy, which will make this concept more concrete. Now, for the combined AB system, we can also define some spin operators. We can identify, for example, an operator for the z component of a given spin I, which is either A or B, and indeed the raising and lowering operators for that spin. Here we're applying these operators to the combined state, one of these basis states that we've just enumerated, but the operator affects only a component of the combined system. For example, SA acts only on spin A of our combined system, independently of what's going on spin B. We can then write down total spin operators, S total Z and S total plus minus, which are simply the sum over the A and B spins of the individual operators. Finally, an important object will be the total spin operator squared, S total squared. This is simply the dot product of the vector operators for S total, and because S total is the sum of A and B, we can write that as SA vector operator squared plus SB vector operator squared plus twice of the dot product between the spin on A and the spin on B. Now, since the individual particles are spin half particles, and S squared acting on a spin half gives us an eigenvalue of S into S plus 1, which in this case is 3/4, these first two terms here just give us a constant. The first one gives us 3/4, the second one gives us 3/4, because each of them is a spin half particle. However, this third term here, SA.SB, is non-trivial. This is an interaction between the two spins. I can write this in terms of the Z components of the operators on A and B spins and the raising and lowering operators. We derived this equation in the last lecture. Now, we can apply these operators to our basis states, and we would find that although these basis states have a definite value of Sz total, meaning that these basis states here are actually eigenstates of the total Sz operator with an eigenvalue of the total Sz, they are not eigenstates of the total spin. If I apply S total squared to these basis states, I would find that, in particular, the up-down and down-up states are not eigenstates of this operator. However, we can define a new basis which are simultaneously eigenstates of the S total squared operator and the S total Z operator. This means that each of the basis states will have a definite eigenvalue for the S total squared operator and the S total Z operator. Therefore, we can label these basis states according to the total spin and total Z projection. These are therefore quantum numbers. Here are the states. We can label them by S total and S total Z. You see here on the right-hand side in the definition in terms of our original basis that we need to take superpositions or linear combinations of our product state basis so that these states are eigenstates of the spin operator. With this definition, it is then easy to check that when we apply S total squared to these states, we get correctly the eigenvalue S into S plus 1 times the state back again. And if we apply S total Z to one of these states, then we get Sz times the state back again. These are the usual rules for the angular momentum operators. So indeed, it makes sense to label these states by the total spin and total spin projection quantum numbers. In particular, we see that we have a multiplet structure. We have a single state with spin 0, this is referred to as a singlet, and then we have a collection of 3 basis states, all with spin 1, with different Z projections, and this is referred to as the triplet state. This all makes good sense from the perspective of addition of angular momenta. You know from the Clebsch-Gordan series that if I take 2 spins 1/2 and I combine them, then I can obtain a spin 0 and a spin 1. And that's exactly what we're seeing here. Let's just quickly remind ourselves of the rules of angular momentum addition in quantum mechanics. The spin projection Sz is an abelian quantum number. This means that it is additive. If I want to know the total Sz, I simply add up all of the Sz's for the individual contributions. For example, imagine that I act on an individual A spin up with the Sa-Z operator, then that's of course an eigenstate of the Sa-Z operator, and it has an eigenvalue of +0.5. If I act on a down state on the B particle with SBZ, then of course I get the state back again with an eigenvalue of -0.5. If I now consider the combined AB system with the state up-down, and I act on it with the total SZ operator, which I can decompose as the sum of the SAZ and SBZ operators, then I have an eigenvalue of 0. So this tells us that the total SZ is 0. It's simply the sum of the individual components. As another example, let's consider this superposition state on the previous slide. This is the one with a total spin equals to 1 and a total Z projection equals to 0 we previously asserted. I'm going to label this with a shorthand notation as the ket 1, 0 for the spin and Z projection. If I apply S total Z operator to this state, I can write that in terms of the individual operators acting on these individual kets, and I will see that because each of them gives me SZ0 in total, by the analogous argument from the line above, then the overall SZ for this combined state will be 0. So here the total SZ is also equal to 0, but it's slightly more subtle because each of the basis states comprising this linear combination here has an S total Z is equal to 0, but you can see that, for example, in this first term, the SZA is +0.5 and SZB is -0.5, whereas in the second ket, SZA is -0.5 and SZB is +0.5. So the state 1, 0 has a definite total SZ equals to 0. However, the SZ of the individual spins A and B is not well defined. If we focus on the A spin, in the first component it's +0.5, but in the second component it's -0.5. So the punchline is that this state is an eigenstate of the total SZ, but it is not an eigenstate of the individual SZs for the A and B spins. By contrast, the spin S is a non-abelian quantum number. It's not simply additive. You might remember from the Clebsch-Gordon series that S1 plus S2 can take different values ranging from the absolute value of S1 minus S2 in integer steps all the way up to S1 plus S2. And for two spin half particles, of course, this implies that we have an S total of either 0 or 1, the singlet or triplet, which is the result that we found directly in the last lecture. So, for example, if I take an upspin on site A and apply to it the SA squared operator, then I get 3/4 times the state back again. This state is an eigenstate of the SA squared operator with an eigenvalue 3/4. That's because we have a spin half particle, and the eigenvalue is S into S plus 1, giving 3/4. Likewise, for a downspin in B, if I apply SB squared, I get 3/4 times the state back again. It's the same eigenvalue because the particle has the same spin independently of the spin projection. On the other hand, if we now apply the S total squared operator to this state, which we introduced on the previous slide, then we get 0. That tells us that we have a total spin of 0. So we have two spin half particles, but when we combine them, we can get spin 0. This is a feature of spin being a non-abelian symmetry and S being a non-abelian quantum number. It's not simply additive. Let's now talk a little more about the underlying symmetries here. If we just consider the S total squared operator, then we see that the three multiplet components of S equals 1 can actually be interchanged by rotations. We can understand this because if we apply the S total squared operator to a state with a definite spin S equals 1, then we will find an eigenvalue of S into S plus 1 is equal to 2, in this case, times the state back again. And that is independent of the S total Z. So whether S total Z is +1, 0, or -1, this relation holds. So we see that all of the three multiplet components of S equals 1 are eigenstates of the total spin operator squared, and indeed they have degenerate eigenvalues independent of the Z projection. You might recall that if you have degenerate eigenstates of a given operator, then any linear combination of those states will also be an eigenstate of that operator. Suppose, for example, that we define a particular linear combination denoted psi, which is going to be a normalized combination of the 1, 1, the 1, 0, and 1, -1 states, Here I'm again labelling the states by their spin and z projection, with arbitrary complex coefficients a, b, and c. Because all of these three components of this linear combination here all have definite spin, we will find that this wave function psi, as defined, is an eigenstate of the total s squared operator. You can try it out yourself to confirm that that's the case. This works, of course, because the s squared operator doesn't care about the z projection, which is different in these three kets. It only cares about the total s, which is the same in all three components. On the other hand, if we were to apply the total sz operator to this state psi, we would find that it is not an eigenstate, and that's simply because this state does not have a definite sz. As you can see here explicitly, it's made up from components with different sz's. In fact, as we'll see, doing this linear combination of these basis states is equivalent to doing a rotation of our coordinate system. In the new coordinate system, we could measure the spin projection sz, and we will find that it would have a definite value. When we talk about the spin projection sz, of course we have some coordinate system in mind, and we can of course do a rotation of our coordinate system to define a new z-axis. Suppose we define a state with definite spin and spin projection, labelled by this ket s with sz, and in this case I'm going to take the triplet of states with s equals 1, meaning that each of these three basis states here has an s equals 1, but an sz of -1, 0, and +1 respectively. So all three of these basis states are eigenstates of the s squared operator with the same eigenvalue s into s plus 1, which in this case is equal to 2. Now suppose we take some arbitrary linear combination, as on the previous slide, where a, b, and c are complex numbers, and this factor at the beginning here is just to properly normalize the state. As I argued on the previous slide, if I apply the s squared operator to this linear combination, I will see that it is an eigenstate with the eigenvalue of 2. It is a state with a definite spin s equals 1. However, we started off with three orthogonal states. The object that I've denoted psi1 here is just a specific linear combination of those states. There must actually, in fact, be two other states, psi2 and psi3, which are mutually orthogonal. To be more precise, what I mean is that since we can take the inner product, or overlap, of these three basis states, and express that in terms of this Kronecker delta, meaning that the states are individually normalized but orthogonal to each other, that implies that if we define this psi1 as this linear combination, there must be two other states, let's call them psi2 and psi3, which are also mutually orthogonal. So is this really the case, and what do these states look like? For example, let's say we take as our psi1 the symmetric linear combination of our basis states. Then I can define explicitly a psi2 and a psi3, defined in the following way, which satisfy this property of orthonormality. I start from a given orthonormal basis of these states, and I end up with a new basis which is still orthonormal. You should check as an exercise yourself that these three states are normalized and that they're orthogonal to each other and therefore satisfy this relation. So we can set up this problem in a more general way by considering it as a rotation in multiplet space. Let's define this vector, psi vector here, as a row matrix containing these three components of our spin 1 multiplet. I can do now a rotation within this multiplet space by simply defining a new vector, psi primed, which is related to the old vector, psi, by multiplying it by this unitary matrix. As I explained in the previous lecture, we want this rotation matrix U to be unitary so that if psi dagger psi is equal to the identity matrix in the original basis, which is equivalent to guaranteeing the orthonormality condition, then psi primed dagger psi primed is equal to the identity matrix in the new basis. And that just follows from the property of the unitary matrix that U dagger U is equal to the identity. So for any arbitrary 3x3 complex unitary matrix, we can define such a rotation. Importantly, this new basis, the one of the psi primed, which will just contain linear combinations of the old basis states by the usual linear algebra of this equation, these will be eigenstates of the spin operator. They will still all have the same spin quantum number, s equals 1. However, they will no longer have definite sz, because we're taking linear combinations of these states with different sz. The point is that this can be viewed as a rotation of our coordinate system for measuring the z projection. We can rotate our operators in a similar fashion, so that when we measure the z projection in our new basis, we again get +1, 0, and -1. Of course, our choice of the z-axis in three-dimensional space is arbitrary. This rotation is basically equivalent to rotating the coordinate system and picking a new z direction. This is an example of a basis transformation, which we began talking about in the previous lecture. Let's now consider the spin raising and lowering operators on these s equals 1 states. First of all, let's denote our states in terms of these kets, labelled by the quantum number for the total spin and total z projection of the spin. For s equals 1, we have sz of -1, 0, and +1. As we saw, these can be written in terms of our composite AB system in the following way. Now, the raising and lowering operators on these states can be thought of as a sum of the raising and lowering operators for the A and the B subsystems. So let's see how these operators act on these basis states. Let's consider, for example, the total spin raising operator S total plus acting on the state 1, 0. Writing out S total plus in terms of SA plus SB plus, and writing out the state 1, 0 as 1 over root 2 of up down plus down up, we have the following expression. Now, some of these terms we can see are immediately 0 because, for example, in this first term, we cannot further raise the A spin because it is already an upspin, and in the second term, we cannot further raise the B spin because it is already an upspin. So these two terms can be immediately crossed out. This, therefore, gives us 1 over root 2 of the term SB plus acting on the up-down state, which gives us the up-up state, and SA plus acting on the down-up state, which again gives us the up-up state. Overall, we have 2 over root 2, which is root 2 times up-up. This is, of course, root 2 times the spin 1 SZ equals 1 state. So we've seen correctly that when we apply the total spin raising operator to our state 1, 0, we generate 1, 1. We get this coefficient here of square root 2. That's actually consistent and correct in terms of the familiar rules of raising and lowering operators on generalized angular momentum states. Suppose I have an angular momentum raising and lowering operators L plus or minus. If they act upon a state Lm, then I get a state Lm plus or minus 1 back again, multiplied by this coefficient. We discussed this in the second lecture, and probably you've seen this from introductory quantum mechanics courses. So in the case of a spin 1 object with Sz component 0, I can raise the Sz component of this to Sz equals plus 1, and if you work this out, the coefficient is indeed square root 2. So all of this algebra actually works out. This tells us something very important, which is that we can think of a spin 1 as really being built up out of two spin-half particles in a symmetric combination. So the triplet state of a combined two spin-half particle system is actually indistinguishable from a genuine spin 1 particle. Conversely, we can say that a spin 1 particle might have a hidden internal structure made up of two spin-half particles. The algebra and the way in which these things transform is exactly the same. These are mathematically identical. Furthermore, the symmetry of a spin 1 particle is indeed the full SU2 symmetry. This is because the spin can be pointing in any direction in three-dimensional space. We saw this explicitly with our rotation transformation within the multiplet space, equivalent to a rotation of our coordinate system. Also, we have the symmetry of Sz going to minus Sz. Together, this gives us the SU2 group, described by the set of unitary matrices encoding the rotations in three-dimensional space. In this case, we have the spin 1 representation of the SU2 group. So what we've seen here is that certain states of a many-particle system comprising entities with particular quantum numbers, for example charge and spin, can behave like particles with different quantum numbers. We start off with 2 spins a half, and we obtain an object that is identically mathematically to a spin 1 particle. This is a general feature of condensed matter physics. One can obtain in many-body systems effective or collective states which behave differently from their individual constituents. In fact, as I hinted, this works both ways. As I'll show later in the lectures, one can start off with particles of spin 1 type and see that in certain conditions, effective spin half particles can be realized. Not as bare particles in the system, but as emergent excitations. This is a simple example of a phenomenon known as fractionalization. This was first discussed by the famous physicist Duncan Haldane in relation to the so-called spin gap problem. In fact, Haldane won the Nobel Prize in Physics for his contributions to quantum topology and fractionalization. Indeed, as we'll see, we can have even more exotic examples of this kind of fractionalization. In fermionic systems comprising electrons in a superconductor, one can obtain so-called Majorana quasiparticles. These are objects which are their own antiparticle. They're kind of like half of a real fermion. These are not the fundamental particles of the system, but they are emergent or collective modes of the system. They are quasiparticles of the system with fractionalized quantum numbers. All of that's to come in this lecture course. Now I want to move on to discussing models of spin systems. What kind of Hamiltonians can we construct, for example, for our system comprising 2 spins 1/2? The simplest kind of interaction between 2 spins is the so-called exchange interaction. The exchange interaction between 2 spins A and B is simply SA dot SB. There is a correction to the energy of the system due to the interaction between the spins A and B following from this term. The parameter J here is just a coupling constant. It's a scalar number which parameterizes the strength of the interaction. It can either be positive or negative, depending on the situation, and J has units of energy. Before I talk about solving the Schrödinger equation for such a Hamiltonian, first let me explain a bit about where this exchange interaction between spins comes from. The microscopic origin of the exchange interaction is basically the Pauli principle and the fermionic wave function antisymmetry. It is called the exchange interaction because it's basically relating to the exchange statistics for fermions. The heuristic argument for the form of the exchange interaction that I've written here goes as follows. The total wave function of a system comprising 2 electrons must be antisymmetric with respect to exchange of those particles. However, the wave function involves a product of a spatial part and a spin part. Therefore, the spatial part must be symmetric if the spin part is antisymmetric, and the spatial part must be antisymmetric if the spin part is symmetric. If the spatial part of the wave function is antisymmetric, then on average the particles are further apart from each other than they would be if the spatial part of the wave function was symmetric. This is basically due to the Pauli principle, as we discussed in the first lecture, and is sometimes called Pauli repulsion. Because the particles have different average separations depending on the symmetry of their spin states, we get different energies for states with different spin symmetry. Exactly how this plays out depends on the details of the microscopic Hamiltonian. For example, the quantum tunneling between particles in different neighbouring orbitals is enhanced by a closer separation. But on the other hand, the electrostatic Coulomb repulsion between the 2 electrons is also larger when the separation is reduced. The important thing to note is that the energy of the system is affected by the spin symmetry. In particular, whether or not the spin wave function is symmetric or antisymmetric with respect to exchange of those particles. Therefore, we will now study the spin symmetry of wave functions involving a system of 2 spin half particles. We will do this using this permutation operator PAB, which will swap the labels of A and B. We then want to ask whether a given wave function is symmetric or antisymmetric under this operation. If I were to operate with this operator PAB on a basis state up, I would like this to return the state up, back again. if I were to act with PAB on down-down, I would like this to return the down-down state. I'm swapping the spin labels of A and B. In these two examples, the spin labels are the same, so I don't see any difference. However, if I act with PAB on the up-down state, this would swap over the labels and I would obtain the down-up state. Likewise, if I act with PAB on down-up, it should swap the labels and I should get the up-down state. This is what I mean by the permutation operator that swaps the spin labels of A and B written out explicitly. The question is, what is this operator PAB? It turns out that this operator yields exactly the right effect when applied to these basis states. 2 times SA.SB plus 1/2. I will leave it as an exercise for you to confirm that this really works. Try, for example, PAB acting on the up-down state, and you will get something like this, which indeed gives us the correct result. So the conclusion of all of that is that the permutation operator that swaps the spin labels is basically this spin-spin interaction, SA.SB. In fact, that's why we call SA.SB an exchange interaction, because it's related to the permutation operator that exchanges the spin labels of two particles. The correction to the energy due to the spin state is basically coming from the exchange statistics of the fermions. We've seen that when the permutation operator acts on these basis states, we swap the A and B labels. For the up-up and down-down states, we see that these are eigenstates of the permutation operator with eigenvalue plus 1. They are symmetric with respect to swapping the spin labels of A and B. However, the up-down and down-up states are not eigenstates of this operator. So let's now instead consider these linear combinations which I introduced earlier, the plus-minus states. These are respectively the even and odd combination of the up-down and down-up basis states. It is then easy to show from these simple properties that if we apply the permutation operator to the plus state, then we get the plus state back again with an eigenvalue plus 1. However, if we apply the permutation operator PAB to the minus state, then we get the minus state back again with an eigenvalue of minus 1. So the plus state is symmetric with respect to exchange of spin labels A and B, whereas the minus state is antisymmetric. So a Hamiltonian of this form, which is referred to as the Heisenberg exchange Hamiltonian, would give different energies for the plus and minus states, because they have different symmetries under exchange of particles. That's because the Heisenberg Hamiltonian here is related to the permutation operator. States that behave differently under the permutation PAB will pick up different energies in this Hamiltonian. Finally, note that the plus and minus states are actually related to the spin eigenstates of our bases. The plus state is the spin 1 SZ0 component, whereas the minus state is the spin 0 SZ0 component. So this Heisenberg Hamiltonian is changing the energy depending on the total spin of the system. So the Heisenberg exchange Hamiltonian for two spins A and B takes this very simple form, and we'll just take J here as some phenomenological parameter. It is determined by microscopic details. It can be positive or negative, but we won't assume anything about it here. Now, earlier in the lecture, we showed that SA.SB can actually be written in terms of the total spin of the system. When we do that, we obtain the following expression. We see 1/2 times J times S total squared minus the constant 3/4 J. Now, the constant here of minus 3/4 J doesn't really matter. It doesn't affect the dynamics of the system because it just shifts up all of the eigenstates by a constant amount. Often, this term would just be neglected from the Hamiltonian altogether. However, I'll keep it in the analysis on this page just so we can compare to the original Hamiltonian involving SA.SB. This alternative expression for the exchange Hamiltonian for two particles is useful because it allows us to immediately write down the eigenstates and eigenenergies of this Hamiltonian. We can do that if we use a basis of states with a definite S total. We spent quite some time in the last lecture developing that basis, so we know what those states are. You've seen these many times by now. I'm simply writing a basis with a definite S total and SZ. In terms of the product state basis that we started with, it has this expression. This is a very nice basis to use with this Hamiltonian, because the Hamiltonian only involves the operator s total squared, and we know how s total squared acts on these states. Specifically, if our exchange Hamiltonian acts on a state with quantum numbers s total and s total z, then we know we will get this state back again, and therefore it is an eigenstate. The eigenvalue is 1/2 j times the eigenvalue of s total squared, which is s into s plus 1. Then we have this correction minus 3/4 j. These states are therefore eigenstates of the Hamiltonian and solve the Schrödinger equation. The corresponding energies are precisely these numbers. Specifically, I obtain the same energy plus 1/4 j for all of the states with s equals 1, independently of their z projection, and I obtain minus 3/4 j as the energy of the spin singlet state with s total equals 0. We see that the three components of the spin 1 state are degenerate. They have the same energy. That is because the Hamiltonian only depends on the total spin s, not on its z projection. Of course, we can lift the degeneracy of the triplet by introducing a magnetic field. The magnetic field couples to the electron spin. Then we would obtain something like this. The Hamiltonian has the same exchange coupling term, but now it is supplemented by two new terms. This B vector here is a vector field corresponding to the magnetic field, and we evaluate it at the position of particle A, and then take the dot product of the vector field with the spin operator. We can do the same likewise for particle B. Note that the B vector here is not an operator, it is simply a vector field corresponding to the strength and direction of the magnetic field at a given point in space. Let's now make a couple of simplifications. Let's assume that the magnetic field is homogeneous and pointing in a particular direction. Let's also say that that direction is the z-axis. Of course, as emphasized earlier, our choice of z-axis is arbitrary, so without loss of generality, we can say that the magnetic field is pointing along the z direction. If the magnetic field is homogeneous, it means it couples with the same strength to the z components of spins A and B. I then obtain this simpler form for the coupling of the magnetic field to our spins. Furthermore, notice that SAZ plus SBZ is actually the total spin projection, S total Z. And indeed, as we saw earlier, we can write the exchange coupling term in terms of S total squared. And so the Hamiltonian can be written in this simple form, involving as it does only the total spin operators S total squared and S total Z. This is particularly convenient because we have a basis of states which are labelled by S total and S total Z. Our basis states are therefore eigenstates of this Hamiltonian. They solve the Schrödinger equation. And the eigenvalue is, of course, the energy, which is simply related to the quantum numbers S total and S total Z. We see that the coupling to the magnetic field introduces this new term in the energy, and this actually lifts the degeneracy of the three components of the spin 1 triplet. The SZ1 component of the triplet now has a correction minus B. The SZ0 component of the triplet doesn't couple to the magnetic field, whereas the SZ-1 component picks up a contribution to the energy of plus B. The spin singlet state, which has S total Z equals 0, again, does not pick up a correction to the energy from the magnetic field. As a function of magnetic field, therefore, we can plot the energies of these states. At B equals 0, we have the spin singlet state with an energy of minus 3/4 J, and then triply degenerate states corresponding to the spin triplet. The SZ plus 1, 0, and minus 1 components are all equal in energy at B equals 0. However, as we switch on the magnetic field, the three components of our spin triplet become non-degenerate. They change in energy in different ways depending on the magnetic field. The SZ0 component does not couple to the field, whereas the SZ plus and minus 1 components have a correction to the energy with an opposite sign. In particular, if I make the magnetic field large enough, I can have a crossing of the ground state from the spin singlet to the SZ1 component of the spin triplet. The change in the ground state of the system happens when the magnetic field is equal to the exchange interaction, b equals j. In the next lecture, we'll actually look at the consequences of this in terms of the physical properties and thermodynamic observables of this system. The previous example of our two-spin system was so easy to solve because we labelled our states by certain quantum numbers, but our Hamiltonian only involved operators for those quantum numbers. In this case, the quantum numbers were s and sz. Of course, this is not the most general scenario, but it does behoove us to think more generally about quantum numbers and how they can be used to help us. We can label an arbitrary basis state phi by a quantum number x if x hat acting on phi gives us the state back again phi multiplied by the quantum number x, and this holds for some generalized quantum mechanical operator x hat. We see that the state phi is therefore an eigenstate of the operator x hat with eigenvalue x. The example given previously in this lecture was sz total, which is built out of saz and sbz, acting on, for example, the up-up or up-down states. These are both eigenstates of s total z with eigenvalues 1 or 0. Importantly, we can label eigenstates psi of a given Hamiltonian h by the same quantum numbers if and only if we can form a simultaneous eigenbasis of h hat and x hat. This can be done if h and x commute, that is, if the commutator of h with x is equal to 0. Only then are the wave functions that solve the Schrödinger equation for a given Hamiltonian h also eigenstates of our quantum number operator x hat, and therefore only in this case can we label our eigenstates psi by the x quantum number. As a concrete example used already in this lecture, let's say that we have some states psi labelled by the quantum numbers s total and s total z. These have corresponding operators, which are s total squared and s total z. Now, for a given Hamiltonian, for example the one that I've written down here from earlier in the lecture, we can check to see whether our quantum number operators commute with this Hamiltonian. In the case of the quantum number corresponding to the total spin, s total squared, the commutator with the Hamiltonian takes the following form. We can write it in terms of these two separate commutators, one involving the commutator of s total squared with itself, which of course is equal to 0, and the other one involving s total z with s total squared. And we know from the rules of angular momentum that actually these again do commute. So this whole thing is equal to 0. This tells us that we can label the states of our Hamiltonian according to s total squared. Likewise, the operator for s total z also commutes with the Hamiltonian, as we see explicitly here. This tells us that we can label our eigenstates of the Hamiltonian psi in terms of our quantum numbers s total and s total z. Indeed, we showed explicitly earlier in the lecture that this is the case. The wave functions that solve the Schrödinger equation for this Hamiltonian can indeed be labelled in terms of their total spin and total spin projection. This is because quantum numbers are conserved quantities. They are not changed by the Hamiltonian. The quantum numbers do not change under the dynamical evolution of the system. This follows from the property that the total time derivative of the quantum number operator x hat is equal to 0. This would therefore imply that the corresponding quantum number x is a conserved quantity that does not change in time. This is important because it implies that we can label our states according to this quantum number. The Hamiltonian does not change the quantum number, and it remains fixed and constant throughout the dynamical evolution of the system. In quantum mechanics, you might recall that the time derivative of an operator is actually given by I upon h bar of the commutator of that operator with the Hamiltonian. This is an important result for what I'll say in the following, so let me briefly prove this result. In the Heisenberg picture, we have a time-dependent operator x hat of t, which is given in terms of these time evolution operators, e to the iht upon h bar and e to the minus iht upon h bar. This is for, of course, the case where the Hamiltonian h is time independent. We can now simply go ahead and take the time derivative d by dt of this operator x of t using the product rule. We have to be careful, however, with the order of these operations. For example, in this first term, I am taking the time derivative of the factor e to the iht upon h bar, and I can pull out to the front the constant ih upon h bar. But in the second term, when I pull this out, I have to keep the order of these operators intact, with x coming before h. But h and e to the iht upon h bar do commute. This is because I can do a Taylor series expansion of this exponential here. I would then obtain 1 minus iht upon h bar plus 1 over 2 factorial of iht upon h bar squared, and so on. Now h obviously commutes with each of these terms because we just have powers of h as the only operator featuring in this series. That implies that I can commute the h through this exponential factor and obtain this as the second term. Now I can identify this cluster of terms e to the iht x e to the minus iht in both of these two terms as simply the time evolved x of t from our original definition. This gives me I upon h bar of h times x of t minus x of t times h. And of course this gives I upon h bar of the commutator of the Hamiltonian with the operator x as originally advertised. Okay, so let's use this important result to say something about conserved quantities and quantum numbers. Since the time dependence of an operator x involves the commutator of the operator x hat with the Hamiltonian, we can see immediately that quantum numbers must commute with the Hamiltonian. That's because, as defined here, quantum numbers correspond to conserved quantities. The quantum numbers do not change with time, and therefore the corresponding operator must commute with h. This tells us that we can label the eigenstates of h according to the quantum number x. If h and x commute, then d by dt of x is equal to 0, meaning that there is no time dependence of the corresponding eigenvalue x. It is constant in time, and therefore a conserved quantity. The Hamiltonian operator does not change the quantum number x when it acts on an eigenstate, therefore we can use the eigenvalue x to label these states. Indeed, we can label a given state by several quantum numbers if their operators all mutually commute, and of course commute with the Hamiltonian. We also saw an example of this in our two-spin system because we were able to label our eigenstates not just according to the total spin, but also according to the total spin projection. We had two quantum numbers with which to label the states. These quantum number operators commuted with each other as well as with the Hamiltonian. As we will see in the next lecture, we can exploit quantum numbers to help us to solve the Schrödinger equation. These quantum numbers also correspond to the conserved quantities in the system and are therefore physically important objects in their own right. Finally, in this lecture, let me briefly touch upon the Heisenberg model for spin systems. Here I'm writing down the general form of an exchange Hamiltonian between a pair of spins I and j, with an exchange coupling j, ij, and now I'm summing over all pairs of spins in the system I and j. Here I could imagine having a large system of spins, not just one or two spins as we've considered so far, but many spins, indeed maybe even in the thermodynamic limit of an infinite number of spins. As before, I can now introduce the total spin operator as just the sum over all of the individual spin operators for all of the individual sites labelled by I, and likewise for the z projection of the total spin, I can just express that as the sum over all of the individual z components of the spins Siz. It is now easy to show that the operator for S total squared and the operator for S total z both commute with this Hamiltonian. These commutators are equal to 0. I will leave that as an exercise for you to check yourselves. That tells us that the total spin and the total spin projection are again good quantum numbers. These are conserved quantities that are not changed by the Hamiltonian. This means that we can label the eigenstates of our Hamiltonian according to S total and S total z. The problem is that the Hamiltonian h is not written simply in terms of these quantum number operators. Therefore, an arbitrary basis labelled by the total spin and the total spin projection will not in general be eigenstates of this Hamiltonian. we have to find a systematic way of solving the Schrödinger equation and working out what the eigenstates are. We know that these eigenstates can be labelled by S and Sz, but what are these eigenstates? How does labelling our basis states according to S and Sz help us in this task? This is going to be the topic of the next lecture.